All right, let's get started with the next topic. We have gone through all kinds of different differential equation solutions so far. We started with ones you can integrate very simply to get to an answer. We did linear, we did separable, we talked about exact, we talked about what happens if an equation isn't exact and tried to make it exact, and if it can be turned into an exact, then you can solve it like an exact. That was the last video. That was a tough one, so try your best with it if you haven't watched it already. There's one more kind that we want to do after all of this, and it is to use substitutions to solve differential equations. The, the spirit behind this is really similar to doing substitution style integrals. So that's kind of where I wanted to start talking about this to kind of justify. I'm breaking this topic up into two videos because there's two kinds of substitutions that I really want you to attach to. So they're going to be, I think, pretty short videos, but let's see. So back when we were learning antiderivatives, or integration, back in first year calculus, we sometimes use a substitution to convert a difficult looking integral into an integral that is easier to solve. And as a matter of fact, we can do the same thing with particular kinds of differential equations. So no matter what kind of substitution you use, the flow is kind of the same. As I said, there are two different kinds of substitutions that I'm going to have you be responsible for, but I could really give you any substitution when it comes to a test, and you should be able to navigate it using these exact same sorts of ideas. So the first thing you want to do is introduce a new dependent variable. Oftentimes, same as like integrals, u or v is often used for that new dependent variable. And you want to introduce a new one that involves the original one in a way that will make the differential equation simpler. Once you've got that, you're going to build the rest of your differential equation out of that new variable, making sure that the original one is nowhere to be seen in the new differential equation. It's kind of like doing an integral using substitution. You don't want to like substitute part way and then have both variables going on at the same time because the integral is not well defined that way. And usually that will lead to a giant disaster. Same thing here. You'll want to convert completely from the old dependent variable into the new one in order to go forward. But to make that conversion, especially to replace derivatives, you absolutely can't forget chain rule, which lots of people tend to do. We're going to see that in a couple of different contexts to make sure that we get this right. Once you've got that simpler DE, find the general solution. And that might involve all sorts of stuff, right? The new equation you get to could be linear. It could be separable. Hell, it could be exact, right? You have all sorts of different techniques we've talked about. So this is an idea where you're taking a tough differential equation, changing it into one that we can handle using other techniques we've done, solving it there, and then converting back. That's our last step. So convert back as a last step to the original dependent variable. And yeah, any kinds of substitutions could be used, so you be prepared, understand the steps so that you can handle anything that I throw at you. But as I said, there are two different kinds of substitutions that I want you to be able to check on your own without me prompting you. And the first one is this. It's substituting y of x equals v of x times x. So this is a substitution that's basically going to take an old variable y and change it into a new one that's defined by having an extra x attached to it in this interesting way. And it turns out that doing this can help you solve a whole class of different kinds of differential equations. There's a weird name for these, but I'll get to that in a second. So we have an equation here. It is dy dx equals x cubed plus 2x squared plus y all over x. If you look at this, you might be able to spot that this is actually a linear differential equation. So if you like, try to solve this using old methods as well, but we'll have a new one to work with here. Okay, so we're going to try this new substitution, y equals v of x times x. Okay, my goal is to replace anything that looks like a y with this quantity that depends on, that's a v instead, right? I need to be able to replace all y's so that only v's appear, and x's as well. So y equals vx, I'm going to be able to put vx where the y is. That's great. But I need an expression for dy dx that appears here. I need to get rid of that and express it in terms of v as well. And for that, I need to think of what dy by dx would be given this expression. And well, I have a product of two things that depend on x, so you have to be a bit careful. The derivative will be the derivative of the v, the derivative times the second, plus the first times the derivative of the second, which is 1. So it's v prime times x plus v. Notice I have v of x right here, and I didn't write v of x right there. Don't let that confuse you. I just wanted enough room for this blank. So I have to replace dy by dx with v prime x plus v. If you're really confused, I could actually write dv dx here instead. So maybe I'll do that. dv dx times x plus v. And now what I'm going to do is make the substitution. The differential equation becomes the following. Okay, so the left side, I had a y here, or sorry, a dy by dx right here. That's going to become dv dx times x plus v. It looks like it gets more complicated, so what up? Well, we'll figure out why it gets nicer. On the right, I have x cubed plus 2x squared plus, and then the y we're replacing by a vx. And the whole thing is over x. Here's what's nice about this. Making that substitution puts an x in every single component, in every single term, rather, in the numerator of that expression. And so because of that, I could factor it in x. And as soon as I do that, I can cancel with the x in the bottom. So watch what happens here. I get dv by dx times x plus v equals, if I divide this through, I get x squared plus 2x plus v. And then, hey, look at this magic. I have a v on both sides. I have a v on both sides, and so that's going to cancel. That's nice. And then I have a dv dx times x equals x squared plus 2x. And believe it or not, I can divide off the x. So I get dv dx equals x plus 2 from the looks of it. So I've taken that differential equation that I started with like this y and x's all in that rational expression, and I've boiled it all the way down to dv dx equals x plus 2, which is a not really differential equation. It's one of the very easiest differential equations that we put together, I put together a video for, and that you watched in the very first time that we were solving differential equations together. You can solve this thing by direct integration. So this is not really differential equation from like video 4 or whatever like that. Solvable by simple integration. And that's what we'll do. See, by making that substitution, we get to something that's much easier to work with. And we get to the answer of v equals, and then the integral of this, x squared over 2 plus 2x, and don't forget your constant that's still in play. But the last step here is going to be to convert back. If let's see here, we had y equals vx. So if y equals vx, then that means that v is equal to, well, it looks like y over x. So we're going to convert back. And I guess my solution is going to kind of bleed down here a little bit, but oh, you'll live. Let's see here. We get y over x equals x squared over 2 plus 2x plus c, or y equals x cubed over 2 plus 2x squared plus c times x. And that is going to form our general solution, right? Kind of gives you a funky, different way of approaching this, this sort of a problem, right? It was a linear equation, so you could try it and see that you get to the same kind of solution at the end of the day, but this substitution gives you another approach. So I have a couple of last notes here on this kind of substitution. So generally speaking, when we're changing these y's into v's times x's, it's really useful for tackling differential equations with certain rational expressions on one side. And the reason for that is oftentimes you'll get something like what happened in this last example, right? I changed a y into a vx, and now I have x's that are common to all of the different terms on top and bottom. So I can divide it out and get to something simpler. So that sometimes happens when you see these rational sorts of expressions. You want to view this as if you can change the y's into vx's and get things to, kind of simplify, to collapse down, then that's exactly why you'd want to use this sort of technique. So, yeah, so what goes here? We want the case where if we change y into vx, we get things to cancel. That's what goes here, simplifying the equation. And if that cancellation is not going to happen, it's not the technique to use. It's kind of like, I have a little bit of a long-standing fear. When I was a kid, we had the police come in to our classroom, and it was grade 3 or 4 or something like that, and they gave a presentation on how to deal with fires in your house, like fires when your house is on fire and is burning down. What should you do? And at the time, I'm sure this is still the way. I'm not like an expert on fire control or anything like that, but we were told that there are a few different kinds of fire extinguishers, and this kind is good for like wood fires, and this kind is good for like oil fires, and this other kind is a good fire extinguisher to put out like electrical fires. The problem being that if you use the wrong one in the wrong kind of fire, it like blows up and causes an explosion, so you probably don't want to do that. You don't want to use an electrical fire extinguisher to put out an oil fire in your kitchen, because you might cause your kitchen to burn down. In the same sort of way, you want to make sure that you're using the right substitutions in the problem, because if you use the wrong one, your kitchen burns down. It's a bad scene. Oftentimes, your differential equation can go from bad to much, much worse and become like completely unsolvable. So make sure that you're using the right substitutions, and when you're using those substitutions, that you're using them correctly. So you want to avoid this situation where you use the wrong kind of substitution, or if this cancellation is not going to happen, because it's just going to make the situation more complicated. And so, as a little bit of an example here, if I had a differential equation that was like y prime equals, and let me think for a second, if I had like 2x plus 5y over x minus y, suppose. This is a rational expression, and you see, if I were to change the y's here, so if we changed these y's into x, or vx, I guess, x would be common to all 4 of those different terms, and x would cancel, and it would make things simpler. So x would cancel. Whoops, not up there, down here. X would cancel from all terms, and the dE would simplify. You can have a differential equation, though, that looks really similar to this, but it won't work the same way. For example, if you had here a really similar differential equation, y prime equals, let me write down, say, 2 plus 5y over x minus y. Here, I could do the same sorts of substitutions into the y, but because my 2 doesn't have an x in it, I'm not going to get an x common to everything, and I'm not going to be able to cancel in quite the same way. So I'm going to say here, without the x, this kind of cancellation cannot happen. In that case, you might want to look at some other technique. Maybe you can rearrange it and test for exactness, that sort of thing. So you'll see a couple of examples of this in the for you to try, for you to practice with. but I want you to see how some of the subtle differences of where this technique might provide an advantage and where it probably will not. This last sort of note here at the bottom is kind of a funny thing. Mathematicians are terrible at coming up with names for things, so we call everything the same. Like, there are a billion different definitions for the word, like linear. There are a bunch of different terms like this. Um, anyway, so one of those terms is homogeneous, which is funny because we've already defined this term in the course, and textbooks just love to call differential equations like this homogeneous for some strange reason. I will never call them this because I think it's super confusing. We already understand homogeneous as being if you have an equation in standard form and you have a 0 on the right-hand side, that is homogeneous. That's the way it will always be for us. Okay, that is these y equals vx substitutions. Hopefully that one example is pretty illuminating. Hopefully you're able to follow the stuff at the end. But in the next video, we are going to go over one last kind of substitution that you're going to be responsible for and do a single example of that. So I hope that you'll join me then.